Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on to section 2.6 from your textbook, which is going to begin our investigation of the concept of an inverse of a square matrix. So before we actually formally sort of start this investigation, I'd like to talk a little bit about sort of why this is an interesting question and why we actually want to sort of pursue this line of inquiry. So, let's give ourselves a question to sort of start with here. We're going to let A be an n by n square matrix. And the question we want to know is, will there always be a matrix B such that A times B is equivalent to B times A is equivalent to the identity matrix? In other words, what we're basically asking here, is there a matrix that acts as a multiplicative inverse? You guys know that for real numbers and complex numbers, for scalar values, there are certainly multiplicative inverses. Things like 5 have a multiplicative inverse of 1/5, and when you do 5 times 1/5 or 1/5 times 5, you always get 1. The question is, does that also apply for matrices? We know it's going to be a bit more challenging for matrices because matrix multiplication is non-commutative. Here, saying that 5 times 1/5 is equal to 1, we immediately know 1/5 times 5 is also going to be equal to 1. But back here, we cannot make that assumption that AB is going to always equal BA. So it's definitely going to be a sort of worthwhile question here. Keep in mind also that for scalar values, there is a value out there that does not have a multiplicative inverse. 0, of course, there's no value times 0 that's going to give you 1. So not every number has a multiplicative inverse. That might also be the case for matrices. Maybe not every matrix has one. So we'll have to investigate this question. So you might ask yourself, why do we care about this question? Well, we could make the argument that we care about this question because it's the next topic that we need to do for our course. But maybe we should give a slightly better answer than that. The first reason that we should care about this question is that it could help us solve systems. If such an inverse matrix did exist, and we had the system AX equals B, then we could use the inverse to solve the system. How do we mean by that, or how would we do that? Well, if we had AX equals B, and imagine that this inverse matrix did exist, right? Let's call the inverse A with a little -1. That'd be notation that we'll introduce in a little bit. Let's imagine multiplying both sides of this equation by that A inverse. So we would get A inverse AX equals A inverse little b. Now, of course, this A inverse is taking the place of this matrix B, and you'll notice that if you have B times A, under the assumption that it's the inverse, that's the identity matrix. So this would become the identity matrix times X equals A inverse B. And then that would tell us, well, the identity matrix times anything is going to just be that same thing. So it's going to be X equals A inverse B. And that's our solution. So if we were able to know the inverse of a matrix, then if we had a system which involved that matrix as the matrix of system coefficients, then we could use that inverse to very easily solve the system through matrix multiplication. We'd multiply the inverse with the system constants, and that would give us the solution. Notice this would also tell us that this is going to be the unique solution, which is something we'll explore a little bit more. So, being able to invert a matrix has a direct relation to being able to solve the corresponding system. Now, this is one reason why we should definitely explore this question, but I actually believe that there's sort of a second, even more general and bigger reason why studying the inverse of a matrix is worthwhile. More fundamentally, the real reason we care about this is because we want to study if these matrix operations we've defined really parallel the ones we know for scalar values. What we've been sort of doing is, since we introduced these matrices as these new mathematical objects and sort of defined the operations, addition, scalar multiplication, matrix multiplication, all those types of things, we've been trying to understand what are the similarities and differences between standard scalar addition, scalar multiplication. We found that there's a lot of similarities. We know that there's like the correspondence of a 0 to a 0 matrix. We know there's the correspondence of this identity matrix to multiplying by 1. But we've also found some differences, such as that normal scalar multiplication is commutative, A times B equals B times A, but that's not the case for matrix multiplication. So this is sort of a valid question because we know multiplicative inverses exist for normal scalar numbers, and we'd like to know if that also is true for these matrix multiplication that we've started sort of defining and studying here. So really fundamentally, the reason I think inverses are interesting to look at is because we're really trying to understand with this new object, matrices, and these new operations, how similar is it to our standard scalar operations. Okay, so now that we have some reasons for why we want to investigate this, let's start by trying to get some information or some results regarding these inverses. So the first thing we're going to prove is a theorem about the uniqueness of matrix inverses. So this says let A be an n by n matrix. You'll notice that everything we're doing in this section is always about square matrices because inverses are only well defined for square matrices. There are inverses. You can extend the concept of an inverse to non-square matrices, but then you have to talk about what is called a left and right inverse, and that's a little beyond the scope of our class. If you guys ever take a full class in linear algebra, you would investigate those concepts of left and right inverses. But for us, we want to be able to multiply the same matrix on both sides, as per this definition here. And to do that, to make sure that there's no size issues, we have to have a square matrix. So everything we're doing, always going to be a square matrix. So this is going to be about the uniqueness of these matrix inverses. So we're going to suppose that there exist two matrices B and C such that AB times BA is equal to the identity and AC equals CA equals the identity. Then this theorem says that B equals C. In other words, if a matrix has an inverse, then it has a unique inverse. So again, this theorem basically states that if the inverse exists, then it will be unique. Note, this theorem does not guarantee that the inverse of a matrix exists. Right in the supposition for the theorem, it says, suppose that these exist. So again, this is saying that if the inverse does exist, then it'll be unique. In other words, each matrix only has one inverse, if any. There's no matrix out there that has two inverses or an infinite number of inverses. All right, let's see if we can come up with a proof for this. So what do we need to show? We get to assume these statements up here. So we get to assume AB equals BA equals IN. And we get to assume that AC equals CA equals IN. So we get to assume these things here. And what we need to show is we need to show that B equals C. So let's start with one of these suppositions. Maybe let's go ahead and say that AB is equal to the identity, right? We know that we can sort of start with that. Let's go ahead then and we'll multiply both sides of this matrix by the other one that we're trying to involve here. So let's go ahead and multiply both sides by C, and we'll do this as a left multiplication. So we would get CAB equals CIN. Right? If this is valid, then certainly multiplying both sides on the left by C, because remember, matrix multiplication is not commutative, so if you multiply a matrix, you have to do it on the appropriate side. Okay, so this would definitely be true. Now this right-hand side, we could, of course, simplify as just C. So we have CAB is equal to C. Then, on this left-hand side, well, notice that we could sort of gather, since we know matrix multiplication is associative, and we could view this as CA B equals C. And then by assumption, CA is equal to IN, so we can replace that as INB is equal to C. And then, of course, IN times B, that is B equals C. And notice that's exactly what we needed to show. We started with AB equals IN, manipulated it, got down to B equals C. So there we go, check mark, QED. So this guarantees us that if we are able to find the inverse of a matrix, that inverse will be unique. Okay, so that's a very important result because that means that if these inverses exist, then we can talk about the inverse. Not we'd have to talk about a inverse, we can talk about the inverse of a matrix. Okay, so let's introduce a little bit of notation now that we know that if the inverse exists, there's only going to be one of them. So let's let A be an n by n square matrix. Then the inverse exists. We notate it with a to the negative 1. This doesn't mean 1 over a. It's not like that. It's not treated as a negative exponent, but this is just our notation for the inverse. Then this matrix will have the property that a times a inverse, or a inverse times a, is equal to the identity. Again, doesn't matter the order in which you do the multiplication. It's always going to result in the identity matrix. A little bit of terminology. Newer sort of textbooks refer to a matrix as either being invertible if it has an inverse, or being non-invertible if it does not have an inverse. Older textbooks refer to being invertible as non-singular and non-invertible as singular. So just be aware that if A has an inverse, then we can either say that A is invertible, or we can say that A is non-singular. And if A does not have an inverse, then we can say A is non-invertible or A is singular. So these are just some different terms you might see, depending on if you look in the textbook, you hear what I'm saying, or if you look online at other resources. Just be aware there's several terms that sort of mean the same thing here. Okay, so now we have this idea of what is it, how do we notate an inverse, and some terminology about that. So let's go and look at a couple little examples here about inverses. So as an example, let's take this square matrix and we're going to verify that A inverse is equal to this. Notice that this isn't saying that we know how to calculate inverses yet, but this is just making sure that we understand how you would verify that a given matrix is the inverse. So what do we need to show here? Well, technically we need to show two things. We need to show A inverse is equal to the identity matrix, and we need to show A inverse A is equal to the identity matrix. And right now, with the information we have, we actually do need to do both of these because matrix multiplication in general is not commutative. At the very end of section 2.6, so probably towards the end of the next video on section 2.6, we will prove that if this happens, then automatically this happens as well, and we will prove that as a property. But right now, we don't know that, so we do need to confirm both of these separately. So let's do A inverse and see what that is. That would be 2, 3, 2, 2, and then that would be times minus 1, 3 halves, 1 minus 1. So matrix multiplication, this row times this column, that's going to give us a negative 2 and a 3. Negative 2 plus 3 is going to give us a 1. This row times this column, that's going to give us a 3 and a negative 3, which when we add up is 0. This row times this column, that's going to give us a negative 2 and a 2, which when we add up gives us 0. And then this row times this column, we're going to get a 3 and a negative 2. Adding those together, we get 1. And that is the identity matrix. Check. So this direction does yield the identity matrix. Now let's go ahead and take a look at the other direction. So now we're going to do negative 1, 3 halves, 1 minus 1, and then times 2, 3, 2, 2. So this row times this column. So that's going to give us a negative 2 and a 3. Negative 2 plus 3 is going to be 1. This row times this column, that's going to give us a negative 3 and a 3, which when we add up is 0. This row times this column, that's going to give us a 2 and a negative 2, which we add up is 0. And then finally this row and this column, that's going to be 3 and negative 2. Add those together, we get 1. That is the identity matrix. Check. So this tells us A inverse really is minus 1, 3 halves, 1 minus 1. That really is the inverse of that matrix A. Okay. So that's just a quick example to make sure we understand what it really means to be the inverse and how you would verify that computationally. Let's see if we can also prove a little theoretical result, sort of in a similar manner. So, as for this example, we're going to assume that A is a matrix that is nilpotent. If you've looked at some of the suggested exercises, I believe in the textbook and definitely some of the ones that I've written for you guys, you'll see that nilpotent is sort of a special type of matrix. Nilpotent matrices, basically when you repeat multiplying themselves with each other, so when you do A to a power, they eventually become the zero matrix. So, nilpotent of degree 2 just simply means that when you square the matrix with itself, you get the zero matrix. So we're going to show that if A is a nilpotent matrix of degree 2, then the matrix A plus IN has inverse IN minus A. So in other words, if A has this special property, then this matrix will have this inverse. So as a proof here, we need to show two things. We need to show that A plus IN times IN minus A is going to be IN. And we need to show that the opposite direction of the multiplication is going to work too. IN minus A times A plus IN is also supposed to be IN. So we need to show both of those statements. So let's start with the first one. So A plus IN times IN minus A. Let's go ahead and multiply that out. So multiplying these matrices, we're just going to sort of apply FOIL. So if I distribute this onto here, it looks like I get AIN minus AA plus IN times IN minus IN times A. Okay, now let's do some simplifications. A times IN times A, those are of course just A. So we get A minus A times A plus IN times IN minus A. Then, of course, we can just cancel the A and the minus A. So we get minus AA plus IN. Well, let's think about what we can say about these. Minus AA, well, that's just A times A is just A squared. That applies even for matrices. So this is minus A squared. And in times in, I guess you could call that in squared, but the identity matrix times anything just results in that same thing. So this has got to be the identity matrix. Now, at this point, we would be sort of stuck. But remember, we have this assumption that A is a nilpotent matrix of degree 2. So we know, by assumption, A squared is equal to 0. So this is minus 0 plus in, which is going to be in. And if you want, you can just remember that this step right here, this is A is nilpotent of degree 2. That's why we were able to take that step there. So we've just shown that if we multiply the matrices together, this one first, this one second, or this one on the left, this one on the right, we do get the identity matrix. So we're half done. Now we'll go ahead and do the opposite direction, in minus A plus in. Hopefully we can do this one a bit faster. Looks like we'll get ina plus in, then minus aa, and then minus ain. Let's simplify all of these now that we sort of have an idea about this. In times a is going to be a. In times in is going to be in. Minus a squared minus a. Then, of course, we can simplify, and we get this as in minus a squared. And then the same trick, this is equal to in minus 0. And again, that's because a is nilpotent of degree 2. And then, of course, that is in minus the 0 matrix. That is in. Check. Do keep in mind that these zeros here you're seeing, that's not the number 0. That is the 0 matrix. That's the only way that that operation would make sense. So we've shown that both directions of the multiplication result in the identity. So a plus in inverse does indeed equal in minus a. Check. Okay. So this is just a couple things making sure that we understand what the sort of definition of an inverse really means. Now it's time to actually start exploring which types of sort of matrices have inverses, which don't, and why they would be useful if we did know that they actually had an inverse. So let's continue on a little bit. So our first thing we'd like to do is we'd like to show how, if a matrix is invertible, how it really helps us solve the corresponding system. So we're going to start by proving this theorem. If A is an n by n invertible matrix, then the system Ax equals B has the unique solution x equals A inverse B. So there's technically two things we need to prove in this. We need to prove that this is a solution and this is a unique solution. So we need to show that x equals A inverse B is a solution, then show it's unique, meaning it's the only solution. So let's start by trying to show that it is a solution. So proof that x equals A inverse B is a solution. Okay, so we need to show that this is a solution to this. How do we do that? Well, we just simply plug into here. So the left-hand side would be ax. The right-hand side is just b. The left-hand side then would become A inverse B, because that's what we're plugging in for x, and the right-hand side is still just B. Here, matrix multiplication is associative, so we can view this as A inverse B and B. Then, of course, A inverse, by definition, since A inverse is, we're assuming that A is invertible, so the inverse exists, then we know that this is in times B. And, of course, the identity matrix times anything just yields that same thing, so we get B and B. So the left-hand side equals the right-hand side, which implies that x equals A inverse B is a solution. So we definitely know that if the matrix A is invertible, if we multiply A inverse with the system constants B, then that result will be a solution to the system. Now we need to show that it's a unique solution. So now proof that x equals A inverse B is the only solution. Okay, so let's let y be a solution to A x equals B. So what we need to show is we need to show that y equals A inverse B. So in other words, what we're going to do is we're going to let y be some other solution to ax equals b, and we're going to show that if y is a solution to ax equals b, then y has to be A inverse b. In other words, A inverse b is the only solution. So how do we do this? Well, we would say ay has to equal b, since y is a solution. Right? That's what it means to be a solution. It satisfies this equation. But since A has an inverse, we can multiply both sides by that inverse. A inverse AY equals A inverse B. Since A is invertible, A inverse exists. So we can use it. We can multiply it on both sides. Over here, we can group and get that as the identity matrix times Y is A inverse B. And then, of course, the identity matrix times that vector y is going to be y equals A inverse B. Check. So this system has unique solution x equals A inverse B. So this proof here had two parts. We first proved that x equals A inverse B is going to be a solution, and then we proved that any other solution would have to be equal to that, meaning that there's only a unique solution. So this gives us another sort of result back similar to what we were talking about with the examples about rank in the previous video. We now know that if the system coefficients form an invertible matrix, then that is another way of saying that we know we're going to get a unique solution. Okay, this still doesn't really help us understand what matrices have inverses and which do not. So now it's time to look at our major theorem for this section, which is the theorem that tells us when matrices actually have inverses. So this is sort of the main theorem here. It's got a very simple statement. It just says that if A is an n by n square matrix, then A is invertible if and only if the rank of A equals n. So in other words, a matrix A is invertible if and only if it has full rank. So the rank of A matches the number of rows and the number of columns. Okay, now this, while a very sort of small theorem, is a very, very important one because it tells us that if A is invertible, the rank of A is equal to n. It tells us that if the rank of A is equal to n, then A is invertible. It tells us that if A is not invertible, then the rank of A is not equal to n. And it tells us if the rank of A is not equal to n, then A is not invertible. And how do I know all those things? Because this is an if and only if, meaning you can read the statement this way and you can read it in reverse. So this is a very powerful sort of statement. Unfortunately, since it is a very powerful statement, and since it reads both directions with that if and only if, it actually requires two separate proofs. We have to prove both directions here. So let's start with the sort of easy direction here. So our easy direction, the easy direction is going to be prove if A is invertible, then rank of A equals n. So in other words, the easy direction is going to be the forwards direction of this statement. So we're going to prove that if A is an invertible matrix, then rank of A is equal to n. Then we'll have to do the other direction. So proof. Since A is invertible, A inverse exists. So then consider the system AX equals B for any B. Okay. So we're just going to say since A is invertible, we know A inverse exists, and we're going to consider this system. Now, from the previous theorem, this will always have unique solution. And technically that unique solution is X equals A inverse B. So if we consider this system, no matter what B is, we know it's always going to have that unique solution. From what we just proved back over here, right? We said that if it's invertible, then this is guaranteed to have a unique solution. However, from the theorem in 2.5, AX equals B only has a unique solution if rank of A equals the number of variables. Right? We said that You're consistent if rank of A equals rank of A augmented. You're inconsistent if rank of A equals does not equal rank of A augmented. And the number of free parameters is always based on the number of variables minus the rank of A. So you only get a unique solution if rank of A equals the number of variables. Thus, right, rank of A must equal the number of variables here, which is n. Check. So there we go. We proved the easy direction. We said that if we know A is invertible, then automatically we know that the rank of A is equal to n. So that gives us the forwards direction of this if and only if. Now we have to do the harder direction. For the harder direction, what we need to prove is we need to prove that if rank of A equals n, then A is invertible. So in other words, we need to show the backwards direction. So we're going to get to assume that the rank of A is equal to n, and we're going to need to show that A is invertible. So we get to assume rank of A is equal to n, and we need to show that A is invertible. So in other words, we need to show A inverse exists. If you prefer, you can then say that we need to show there exists A inverse such that A inverse equals to the identity matrix and A inverse A equals the identity matrix. So to do this proof, the only thing we get to assume is that the rank of A is equal to n, and what we need to do is we need to figure out what A inverse should look like, and we need to verify that A inverse has the properties that the inverse matrix is supposed to have, namely that A times A inverse is the identity and A inverse times A is the identity. Okay, so to do this, we need a little bit of sort of a mechanism, just a sort of notational piece. To do this, we're going to begin by defining the following. We're going to define E sub k to be the column vector that is 0, then more zeros, then a 1, then a 0, and let's just give ourselves a little bit more space because that looks sort of ugly there. We're going to define this E sub k as 0, then zeros, then a 1, 0, and then more zeros. And this 1 is in the kth position. So we're going to define this very special sort of column vector. Sometimes you hear these referenced as the elementary column vectors. So they have a 1 in the kth position and zeros elsewhere. So something like E sub 1 would be 1 with all zeros. Something like E sub 2 would be 0, 1, and then all zeros. So we're going to make this definition. Why do we want to do that? Well, one thing is it gives us a nice way of describing the identity matrix. Notice that the identity matrix can then be thought about as having these component columns, E1, E2, all the way down to En. Remember, each of these is a column vector. So if we have each of these as the columns, then that's equivalent to the identity matrix. Okay, so we have this definition, and we want to note the identity matrix is certainly equivalent to this. Okay, let's give ourselves another page and actually continue on here. So now what we're going to do is we're going to consider the system A times x sub k equals E sub k. So we're going to think about the system that uses our matrix A as the system coefficients and has system constants equal to E sub k. What we're going to do is we're going to claim that the solution vector, the column of solution vectors, if we use those as the columns, they form our inverse. So we're going to claim that A inverse is equal to x1, x2, down to xn. So in other words, we're going to claim that our inverse matrix has columns made up of the solutions to these systems. So this is our claim. Now we need to actually start to show those two components. So we have a claim for what A inverse should look like. Now we need to verify that it actually has the two properties that an inverse is supposed to have. Okay. You might ask yourself, how do we know that this exists? Well, how do we know that the system has solutions? So first, how do we know A inverse exists? Well, if you think about that, each x sub k is a solution to ax sub k equals e sub k, which we know has unique solution. How do we know it has unique solution? Since rank of A is equal to n. Remember, rank of A equal to n, we said that if that was true, then this is always going to have solutions, because remember, A is n by n, so A augmented is n by n plus 1. So the rank of A augmented also can at most be n. So rank of A is always going to equal rank of A augmented, so there's always going to be solutions, and since the rank of A matches the number of variables, it's always going to be a unique solution. So we know that these are always going to have solutions. So the x sub k's really do exist. So it actually makes sense that we can actually say that this is going to work. In other words, that we can come up with this x1, x2 through xn. Does that mean that it's guaranteed to be the inverse? No, it just means that what I said here, these things really exist. In other words, my claim actually makes sense as a claim. Now, second, we need to show that A inverse is equal to the identity matrix. So we need to show that it has that first property for inverse matrices, that A times A inverse is the identity. So let's go ahead and do that. So let's take a look at A times our A inverse. So this is going to be A times these x1, x2 down to xn. So how do we do this multiplication here? Well, remember, you take rows of this times columns here. Since you're going to take every row of A times each column individually, that's the same as just multiplying this matrix A onto each of these columns. That's why we define these as being the columns of A inverse. So this is AX1, AX2, down to AXN. So the columns of A times A inverse are AX1, AX2, AXN. Remember, each of these is an n by n times an n by 1. So each of these is an n by 1. Each of these is a column vector. Okay, but what do we know about these? Well, by definition, AXK equals E sub k. So this is equal to E sub 1, E sub 2, down to E sub n. And that, by definition, we said, is the identity matrix. So we're all good. So we've now shown that A times our claimed A inverse really is the identity. Finally, we need to show that A inverse A equals the identity matrix. So now we need to show that the opposite direction of the multiplication also gives us the identity matrix. We're not going to be able to do this trick directly again, because if you think about it, this time the columns would be here, and if A inverse is the first thing, we'd have to take rows of this, which we don't really know much about. So we're not going to be able to use this exact same trick. Instead, we're going to start with the fact that A inverse is equal to the identity matrix. We're going to start with what we proved back up here. Then we're going to go ahead and right multiply by A. So we're going to get A inverse A equals INA. So we can do that. That's just right multiplying by A. Okay? Well, what can we say about this then? Well, on this side, IN times A, that's just going to be A. So we get that this is equal to A. Now, let's bring this over. We can subtract it on both sides and get A inverse A minus A is supposed to be 0. And keep in mind, this 0 over here is the 0 n by n matrix. Okay, now for this, let's go ahead and notice that everything has a leading A, so we can factor that A out, and we'll factor it out on the left. So we'd have A inverse A, and of course when we factor the A out of here, we don't get like minus 1, we get minus the identity matrix equals 0. Okay, so now we have A times this is equal to 0. So what we're going to do is we're going to let A inverse A minus IN equal y1, y2 through yn. So we're going to define this to have these column vectors that we're just going to call y1, y2 through yn. Why am I doing that? Well, because I have my matrix A times these, so I can use my standard sort of trick now. As long as I sort of redefine this like that, we can say that then we have A times y1, y2, yn is equal to 0. So again, we take rows of this and multiply by these columns. So we can just put this onto each of them. So now this has columns AY1, AY2, AYN equals 0. Now this over here is a matrix that has each of these columns is supposed to equal the 0 matrix. So that tells us for every y sub k, we know a times y sub k must equal 0. Now this is actually in terms of a vector equation now. This is saying a times that vector, column vector y sub k, must be the 0 vector. Okay, we're almost there. What can we say about this? Well, this again is a system that involves the coefficients with a. So since rank of a equals n, this has unique solution. But we know a little bit more than that. It's equal to 0, meaning it's homogeneous. So what's the solution for all homogeneous equations? 0. Since it has a unique solution, we know the only solution is y sub k equals 0. So we now know that y sub k equals 0 for all k. All right, so now we know that every one of these actually equals 0. Okay, now we can put this back with this. So let's go ahead. We'll give ourselves one more page here. So just recall, all right, we made this definition here. This is where we got those y sub n's here. Okay, so let's bring this over here. So we had this. Since y sub k equals 0 for all k, so again, that means every one of these columns is actually 0. Then we get A inverse A minus IN is actually equal to 0, meaning the 0 matrix. Now we got one last step, bring that IN over, and we get A inverse A equals IN. And after all that, we give ourselves a check mark, we give ourselves a QED, we give ourselves a smiley face, whatever you like. That was quite a bit, but now we've shown it. If we look back, in this part, we showed 3 things. First, that this x1, x2, xn really makes sense by using the rank of a equals n. Then we showed, by choosing the x1, x2, xn in the way we did, a times a inverse is definitely the identity. And then we did a tremendous amount of work to show that a inverse a, the opposite direction, is also the identity. Notice that in here, we again used that the rank of a was equal to n to guarantee that we'll have a unique solution, so that all of those solutions were actually equal to 0, which meant that we were able, on this page here, to conclude that a inverse a minus the identity was equal to the 0 matrix, which then allowed us to actually get that a inverse a was the identity. So this gives us our main theorem here. So before we sort of move on from here, do keep in mind what this theorem is saying. Since it is an if and only if, you can actually read it either way, and that actually gives you 4 different statements. It says if a is invertible, the rank of a is n. If you can show that the rank of a is n, you automatically know it's invertible. If a is not invertible, then the rank of a will not be n. In fact, you know that the rank of a must be less than n, because it can never be greater than n. And if the rank of a is ever less than n, you automatically know it's not invertible. So this is a very powerful theorem because it reads both ways. Turns out that there's also something else sort of important about this theorem, which is that the way we prove this theorem, specifically this moment right here, where we said let's let A inverse be x1, x2 through xn, where xk was the solutions to these systems, this actually tells us how to find inverses. So as our final idea in this video, we'd like to talk about how we're going to determine an inverse. Now we know what an inverse is. We know which types of matrices have inverses, those that have full rank. Now we need to say how we're going to find those inverses. So determining the inverse of a matrix. So we really use the main idea of the previous proof to actually find the inverse of an invertible matrix. The key idea is that if A inverse exists, then by the previous proof, we can define A inverse to be that x1, x2 through xn, where xk solves that system A xk equals E sub k. Computationally, we can solve these systems at the same time as follows. The big trick here is what you're going to do is you're going to take your matrix A and you're going to augment it with each of these E sub 1s, right? This E sub k's. That means you're going to augment it not with a single vector, but with the identity matrix itself. Then, if you can use elementary row operations to turn the left-hand side into the identity matrix, so if you can convert this into the identity matrix, then that's solving each of the systems. What happens on this side will actually give you A inverse. If it is impossible to use EROs to convert A into the identity matrix, then A is not invertible. How do we know that? Well, if you can't bring A to the identity matrix using elementary row operations, that must mean that along the way, converting A into the identity using those, you must get a 0 row. And as soon as you get a 0 row, the rank won't be full, and that means it's non-invertible. So computationally, as we'll see in the next couple examples, the big trick here is to augment your matrix with the identity, manipulate the left-hand side into the identity, and what you get on the right-hand side will be your inverse. Let's go ahead and take a look at that. So we're going to try to determine the inverse of this matrix if it exists. Again, not every square matrix has an inverse, so along the way, we might find out that the inverse doesn't exist. So to do this, we're going to augment 2, 1, 2, 1, 1, 0, 1, 0, 1 with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, our goal is to change this into the identity matrix and keep track of what happens over here. What eventually will end up over here will be A inverse. So we can make things a little bit easier. Maybe we can move this up to the top. So let's do our first elementary row operation as interchanging row 1 and row 3. So that'll give us 1, 0, 1, 0, 0, 1, then 1, 1, 0, 0, 1, 0, and then 2, 1, 2, 1, 0, 0. Okay, so that's our first step there. Now we have a 1 in that leading position, so we can eliminate the stuff underneath it. So let's go ahead and do sort of 2 operations. Let's take row 2 and replace it with row 2 minus row 1. And we'll take row 3 and replace it with row 3 minus 2 row 1. So 1, 0, 1, 0, 0, 1. Now we're going to subtract, so we're going to get 0, 1, negative 1. And then we're going to get 0, 1, negative 1. Okay, and then here we're going to get 0 and 1. And since we're subtracting 2 row 1, we'll actually get a 0 there. And then 1, 0, negative 2. Okay, so we've got our pivot position there. Now, of course, we could just use this one here, or we could, I guess, flip these 2 up. But I'll just go ahead and use this. I'll just immediately, since this already has its pivot, we can just get rid of that one. So let's go ahead and do R3 and replace it with R3 minus R2. 1, 0, 1, 0, 0, 1, 0, 1 minus 1, 0, 1 minus 1. So we're going to be subtracting, and looks like we're going to get 0, 0, and then when we do 0 minus negative 1, we're going to get a 1 there. And then we're subtracting here, so we get 1, negative 1, and then minus 2 plus 1, so minus 1. Okay, this is technically in row echelon form. So if you notice here, we can get that the rank of A is equal to 3, which tells us that A inverse will exist. So we don't know the inverse yet because this isn't equivalent to the identity matrix just yet, but we do know that A inverse is going to exist because this does have full rank. Now let's go ahead and finish this up. To do this, we need to eliminate these things here. So we can do R2 and replace it with R2 plus R3, and R1 and replace it with R1 minus R3. So let's go ahead and do that. We're going to take this row and subtract here. So we're going to get 1, 0, 0. And then we're taking this row and subtracting here. So it looks like we're going to get minus 1, 1, and then 1 minus negative 1, so 2. Then we're adding this row onto here. So we're getting 0, 1, 0. And then looks like we're going to get 1, 0, and negative 2. And then we didn't do anything to our third row, so 0, 0, 1, 1, negative 1, negative 1. So there we go. Now this is the identity matrix. So this tells us that A inverse actually is equal to the square matrix negative 1, 1, 2, 1, 0, negative 2, 1, negative 1, negative 1. Could we check this? Yeah, if we wanted to, what we could do is we could take matrix A, multiply it with A inverse, confirm that we get the identity, and then take A inverse, multiply it with A, and confirm that we get the identity. You don't need to, because this process does work, but if you ever want to check your answer, that's how you would verify it. Go ahead and multiply this with this, make sure you get the identity, then take this one first, multiply it with this, make sure you get the identity. I would recommend, just for some practice, trying that out on your own. For us, though, we're going to look at one more example of this. So